Hello, Internet! On May 24, 2018, the routing team at Maidsafe released PARSEC, a protocol for asynchronous, reliable, secure, and efficient consensus. I'm Pierre, a member of the routing team and one of the authors of PARSEC. In this video, I'll try to explain what it means exactly and why it is such a big deal. For those of you who want to know everything about it, I'll also explain the algorithm in detail while trying to remain accessible to everyone. PARSEC is a Byzantine consensus protocol. The general problem of Byzantine fault-tolerant consensus is a classical problem of distributed systems. It was first described by Leslie Lamport, Robert Shostak, and Marshall Pease in their 1982 paper, The Byzantine Generals Problem. Put simply, there is a number of computers that we call nodes, which are connected forming a network. They attempt to communicate truths about the network to each other. We call these truths network events. A fraction of the nodes are malicious and are trying to cause dissent amongst the honest nodes. These are called Byzantine nodes. We must devise a strategy for each node to establish the truth and to order the true network events despite the Byzantine node's best attempt to prevent that outcome. There are well-known mathematical proofs from the 1985 paper Impossibility of Distributed Consensus with One Faulty Process by Fisher, Lynch, and Peterson that establish that this problem cannot be solved deterministically in the presence of any Byzantine node. So this means any solution we come up with will have to have some form of randomness. Here at Maidsafe, we are building the SAFE network. SAFE stands for Secure Access for Everyone. It's a network that connects individual networks' computers in a way that they can store their data while keeping full ownership of it, removing the need for centralized servers. The network does much more than simple data storage, as it also enables all kinds of applications such as social networks, messaging applications, decentralized exchanges, and much more to be developed. If you're interested in learning more about the full potential of the SAFE network, a good place to get started would be by reading the SAFE Network Primer that you can find at safenetworkprimer.com. Our decentralized network is split in groups that we call disjoint sections. This is our way of handling what some other applications refer to as sharding. This allows the network to sustain a very high activity while spreading the load somewhat evenly in the network. As the nodes are individual users' computers, we can't expect very high reliability from them. So we can expect nodes potentially disconnecting from the network and reconnecting on a regular basis. This process is called churn, and the network must handle churn gracefully. Also, because the network is composed of individual users' computers, we can't rely on the connection between nodes to be homogeneous. That means that some nodes could communicate between themselves much faster than some other nodes. This property of a network is called asynchrony. The truths that we want to maintain between nodes of the network is which other nodes are currently connected to their section of the network. Because access to the SAFE network is unrestricted, we fully expect a fraction of the nodes to exhibit Byzantine behavior, their only objective being to try and damage the network. This explains our need for Byzantine fault tolerance. Finally, the source code for the SAFE network is developed openly and available to anyone to audit, as this is the only way to prove security claims to our users. This means that any consensus algorithm we use must be fully open, which prevents us from using patented solutions. So, The category of Byzantine consensus we need is asynchronous Byzantine fault-tolerant consensus, ABFT. Academic work on obtaining consensus has boomed in recent years, especially since the invention of Bitcoin and the explosion of cryptocurrencies. We will consider a few alternative algorithms and establish why none of them were adequate for use in the safe network, which prompted us to come up with our own solution. In fact, the backbone of Bitcoin, the blockchain, is a solution to the Byzantine generals problem that offers consensus with high probability by using the proof of work mechanism. Proof of work requires every participant in the consensus process to burn so much energy that it would be impractical for Byzantine nodes to take over the network. Proof of work-based solutions cannot work for the safe network, as they lead to the centralization of power to the network participants that can afford burning very high amounts of energy to participate in the consensus process. It also doesn't offer consensus fast enough, in practice, to cope with the need for speed from the safe network. In 2016, Swirls released a closed and patented algorithm called the HashGraph that solved the asynchronous BFT problem in a rather elegant fashion, using the well-known concept of gossip to solve it in a very asynchronous and resilient way. There are a couple of issues with the approach. The algorithm, as they describe it in their paper, cannot be proven to produce consensus in a finite time in the presence of a sophisticated enough adversary that controls less than a third of the nodes. It could, in theory, be made to handle that situation by using an algorithm called a common coin, but this algorithm in itself presents its own set of challenges. Of course, another major issue with this approach is that it is patented, which rules it out as a candidate for the safe network, since all our code will be released under the GPL v3 license. Another solution from 2016 is Badger BFT. It's an algorithm that is composed of many existing algorithms, which provides ABFT consensus with high probability. The two main problems we have with this algorithm is that it is rather complex. Also, like the HashGraph, it requires the use of a common coin algorithm. The problem we have with the common coin algorithm is that existing implementations generally require a trusted setup phase every time the participants of the network change. This trusted setup phase is generally synchronous. In the safe network, with the high churn that we expect, it would make it very hard to use Badger and have it behave effectively asynchronously. For completeness' sake, there is a way around that issue called distributed key generation, but this solution adds another layer of mathematical complexity to an algorithm that is already quite complex. We could have used Badger BFT with distributed key generation, but we found a more elegant solution. PARSEC, a protocol for asynchronous, reliable, secure, and efficient consensus, is the most elegant solution to the ABFT problem in existence today. Unlike the HashGraph, it is fully open, and it can be proved that a Byzantine adversary cannot stall consensus for an arbitrary long time. It is mathematically much less complex than Badger, and consensus can be proven with probability 1 instead of relying on high statistical probability of consensus. Unlike the blockchain, it is efficient and does not sacrifice users' computing resources on the altar of security. We released all the details about the algorithm in a request for comment and redacted a concise white paper that demonstrates mathematical proofs for all the algorithm's properties. Now we have covered a bit of the historical background and hopefully conveyed the unique qualities of PARSEC. It is time to dive a little bit deeper. I will now proceed to describe our algorithm, first at a high level as a composite of simpler pieces. I explain how each of the pieces works and attempt to convey the intuition behind the mathematical proofs where possible. As advertised, the algorithm is rather elegant and simple, which gives me confidence I will be able to convey all these ideas without having to dive too deep into nasty mathematical concepts. At a glance, PARSEC is mostly based on two main ideas. One such idea is gossip, which is a very efficient way for nodes to communicate between each other. It is the backbone of a few modern consensus protocols, such as the HashGraph and Avalanche. Another key idea behind our solution is that of asynchronous binary agreement, or ABA. This piece of the puzzle is like the general ABFT problem that PARSEC solves, except agreement can only be reached on a binary value. A binary value is a value that can only be true or false, like the answer to a yes/no question. We take heavy inspiration from a paper by Mostefari et al. That gives an elegant solution to ABA. As hinted, our algorithm is deeply rooted in gossip. I will now explain what this means. Gossip is a way for a network of computers to exchange information very efficiently by emulating the way rumors spread in human societies. For a rumor to spread, everyone does not have to tell everything they know to everyone. Instead, two individuals meet and exchange the freshest news they've got. They then go on to meet other individuals in their circle of friends and inform them of what they have learned. Intuitively, it is easy to see that it is much more efficient than trying to gather the entire town in the same room at the same time and have everyone tell everyone else everything they know. But pictures speak louder than words, so let me explain with an example. Here, we call our nodes Alice, Bob, Carol, and Dave. They are ready to gossip to each other. The rectangular-shaped boxes represent everything they know until now. Alice randomly selects Bob and lets him know all that she knows. Bob records this by creating a gossip event. Now, Bob received a gossip request from Alice. He has a duty of gossiping back to her as soon as possible. But because the network is asynchronous, before Bob is able to do that, Dave randomly gossips to Carol. This is also a request that requires Carol to answer as soon as she can. Now, Bob gets to send a gossip response to Alice. The arrow is colored green to illustrate the fact that this is a response. He informs her of all the information that was in his rectangle, but not in hers. She records this by creating a gossip event and adding it to her gossip graph. Carol now gossips to Alice. At this precise moment, Alice has seen every gossip event that took place in the network. However, she has no way to be aware of this fact, as from her point of view, any communication could have happened between other nodes after the latest event she recorded. If she hasn't seen some of the gossip, though, she knows she will receive it eventually. In fact, it is proved that everyone's gossip graph will be the same eventually, which is the only property we need. Now, Dave created a gossip event that has no incoming arrow from another node. This means that he created this gossip event to record an observation that he made himself in the network. Dave randomly gossips to Bob, who now knows what it is that Dave learned. Carol responds to Dave's earlier gossip, and Dave records this in his gossip graph. Bob responds to Dave's earlier gossip, and Dave records this in his gossip graph. We will stop here, as more gossip would conveniently have a hard time fitting on the slide. But in our protocol, this process keeps going with time, and each node's gossip graph keeps growing forever as the gossip protocol continues. Now let's use this example to define a couple of properties of gossip that will come in handy for us. Here, we arbitrarily give a name to two events, B2 and D0. We say that B2 sees D0, as there is a directed path through the gossip graph going from D0 to B2. Here, we define the concept of a gossip event strongly seeing another event. A gossip event strongly sees another gossip event if a number of directed paths exist between these gossip events that together pass by a supermajority of nodes. A supermajority means more than 2/3 of the nodes. So in this example, that would be 3 nodes. Note that here, B2 doesn't strongly see D0 anymore, as all the paths between B2 and D0 only pass by Bob and Dave. That's only 2 nodes, which is less than a supermajority. However, we can see that A2 strongly sees D0, as the only path between A2 and D0 passes by Alice, Carol, and Dave, which is a supermajority. Note that it doesn't have to be only one path. For instance here, D3 also strongly sees D0, as considering all the paths between D3 and D0, these paths contain gossip events created by Bob, Carol, and Dave, which constitutes a supermajority of the nodes. To sum it up, gossip is a way for nodes, another name for computers, to communicate with each other to spread information in a network. It does not require all computers to communicate everything they know to all other computers, which is extremely important for scalability. It is a natural way to communicate asynchronously. Each node constructs a gossip graph from recording everything they are being told by other nodes. Eventually, all nodes will hold the same gossip graph. Looking at a gossip graph from any node's perspective, we can establish relationship between gossip events. 2 such relationships that we described are the concept of an event seeing another one and the related concept of an event strongly seeing another one. So far we have described gossip, which gives us a way to communicate and establish a common history of events in a gossip graph. We also have brushed on the abstract concept of Byzantine consensus. However, there still remains a large gap between gossip and agreeing on a certain order for all events. To bridge this gap, let's define one extra concept, that of an interesting gossip event. We must recognize that not all gossip events are made equal. Some may be more interesting than others. In the specific context of the safe network, these are the gossip events that turn a block valid. Understanding what exactly makes a block valid is not necessary to understand PARSEC, so I will refer the keen listeners to the request for comment for more details on this part. In a more general context, interesting gossip events could be those that carry a vote for a certain action, or more generally a certain kind of information. In short, what makes a gossip event interesting is the information it carries. That information is the one that we are trying to order via Byzantine fault-tolerant consensus. With this context of interesting gossip events in the gossip graph, the Byzantine consensus can be expressed as follows. As a node looking at its gossip graph, I may see a number of interesting gossip events. I am asked to pick the next interesting gossip event to be agreed on. If I feel I don't have enough information yet, I can simply pass my turn. I will then try that game again after receiving more gossip. However, if I give an answer, I must be sure that any other node that is not Byzantine, that's any other good guy if you prefer, will pick the interesting gossip events in the same order. Note that once I pick an interesting gossip event and decide it to be the next one, it becomes boring, as new shiny things are always more exciting. Okay, we rewarded the problem of Byzantine consensus to apply in the context of gossip. That's a good beginning, as gossip has some great properties, two of which are it scales well, it is an effective way to express asynchrony. Now, the problem is still pretty hard to solve as is, so we'll do what us computer scientists do best: reduce the original problem to a simpler one, and try to solve that instead. More specifically, we will reduce the problem of reaching consensus on the order of any kinds of events to that of reaching consensus on a binary value, a 0 or a 1. That simpler problem is called binary Byzantine consensus. I will have to define two concepts before we get there, so buckle up and follow me. The first of these two concepts is that of observers. Observers are gossip events, but not any gossip events. They have the particular property that they can strongly see interesting gossip events created by a supermajority of different nodes. I know that sounds a bit abstract, so cue the illustrations. Consider this particular gossip graph. Consider that each rectangle gossip event is an interesting gossip event. The gossip event labeled D3 is an observer. Let's prove it to ourselves. The gossip event D3 sees Dave's interesting rectangular event through passing by Bob, Carol, and Dave himself. That's 3 out of 4 nodes, which is a supermajority. D3 strongly sees Dave's rectangular events. D3 also strongly sees Alice's rectangular gossip event, as it can see it through Alice, Bob, and Dave. Finally, D3 strongly sees Carol's rectangular gossip event through Bob, Carol, and Dave. So D3 strongly sees Alice, Carol, and Dave's rectangular events. It strongly sees interesting events created by a supermajority of nodes. Hence, B3 satisfies our definition of an observer. An interesting fact about gossip is that as the gossip graph progresses, any gossip event created by a honest node will eventually be seen by an observer. Now we have defined an observer. We need to explain one more concept, and then promised we'll transform Byzantine consensus into binary Byzantine consensus. The additional concept to be aware of is that of a meta-vote. Every time a node, say Dave, tries to find the next interesting gossip event, they can cast a meta-vote for any node, say Alice. Dave's meta-vote for Alice is the answer Dave gives to the following question. Does my oldest observer strongly see an interesting event that was created by this node? So, does Dave's oldest observer strongly see an interesting event that was created by Alice? Yes, it does, as we saw a few slides ago. Dave's meta-vote for Alice is true. Does Dave's oldest observer strongly see an interesting event that was created by Bob? No, it doesn't. I've highlighted all the directed paths between D3 and Bob's rectangle gossip event. They only pass by Bob and Dave, which is less than 2/3 of the nodes, so not a supermajority. Dave's meta-vote for Bob is false. I've been promising to reduce Byzantine consensus to binary Byzantine consensus after 2 additional definitions. I've had my definitions, now it's time to deliver on my promise. We mentioned before that reaching consensus by looking at a gossip graph was akin to naming the next interesting gossip event to be considered, agreeing on which is the oldest among all nodes. Of course, the next interesting gossip event could be or contain anything, so this describes a full consensus. Now, here is a suggestion. Wait until the gossip graph contains enough observers and then reach agreement on the value for each meta-vote. That value is the answer to a true-false question, so it is a binary value. Now, how do we get from these instances of binary agreement back to the full consensus we are aiming for? Here is how. Once everyone agrees on each meta-vote, select each node for which the agreed meta-vote is true. Consider the oldest interesting gossip event from each of these nodes. Looking at the content of these gossip events, if they carry more than one arbitrary value, pick the most represented value. If there is a tie, sort the events, for example lexicographically, and pick the highest value. So every node will eventually see at least one honest observer of the oldest interesting event that was created by the node whose meta-vote was true. Hence, every node will be able to apply the voting process described earlier. Now there is one final way this procedure could go wrong. What if all meta-votes agreed on were false? No decision could be taken then. Luckily for us, because of the way we defined observers as strongly seeing interesting gossip events created by a supermajority of nodes, each of them will cast less than 1/3 false meta-votes. Altogether, it is not enough false meta-votes for agreement to be reached on false on all of them. So there you have it, binary Byzantine consensus from full Byzantine consensus. And it wasn't even that hard. Now, how do we even solve binary Byzantine consensus? Before we get there, let me explain exactly what we are looking for. Binary Byzantine consensus is defined as having 4 properties. Validity. A decided value must have been proposed by a correct node. Agreement. No 2 correct nodes must decide different values. I bet you could have seen this one coming. One shot. a correct node must decide at most once. Termination. Each correct node must decide a binary value eventually. So far, we have been able to express the problem of Byzantine consensus in terms of gossip, which is very useful for its asynchrony and efficiency. We have then reduced the problem to that of reaching binary Byzantine consensus on the observer's metavotes. We have explained why that would indeed solve the problem. We have described the exact properties of binary Byzantine consensus. Let's address the elephant in the room. How do we solve that simpler problem? Well, we don't live in a vacuum. There actually happens to be an elegant solution to asynchronous Byzantine consensus already, from Mostefari, Moumen, and Reynal. Now, let's bisect the title of their paper. Signature-free sounds like a nice property. Signatures are maths, and who in their right mind likes doing math? Asynchronous Byzantine consensus, bang on. That's exactly what we were looking for. They don't say explicitly in the title that they're only covering binary consensus, but that's what they do. With t lower to n divided by 3. T is a common way to refer to the number of Byzantine processes. T lower to n divided by 3 is the very best result that's mathematically possible with a signature-free scheme, so that's great. And O of n square messages. O of n square messages is a measure of amount of work that needs to be done to reach consensus. Now, when this paper was released, this was really good. It meant that with all nodes connected to each other, you only needed to send a constant number of messages between each node. Because the full title is a bit of a mouthful, I will sometimes refer to it as ABA for Asynchronous Binary Agreement. Well, ABA was released in 2014, before the HashGraph and before the Avalanche paper had been released. So, that was before the idea of applying gossip to the Byzantine consensus problem had become popular. By adapting their key ID to gossip, we can do better than O of n squared. In fact, we can reduce the number of messages needed to O of n log n. To give an idea of the difference, for 1,000 nodes, n squared is around 1 million, whereas n log n is around 3,000 messages. The larger n gets, the more dramatic this difference becomes. Now, to describe the key idea behind ABA, they do the same thing we did with our observers and metavotes. They reduce the problem of binary consensus to a simpler problem, called a common coin. A common coin is an imaginary device that all nodes could flip at any time asynchronously. They would be guaranteed to have a result, head or tail, that is the same for any node taking part in the process, but that is not predictable by any node before a certain number of nodes started flipping the coin. We found that problem to be too complicated, so we ended up simplifying that too. But for now, it is sufficient to understand that a common coin is simpler than binary consensus. So, let's show how we can convert binary consensus to a common coin. Because we're demonstrating PARSEC, we'll go straight away to the gossip formulation of ABA. If you're interested in the original with broadcast, I invite you to read the 2014 paper. So the main tool that ABA describes for reducing binary consensus to a common coin is what they call binary value broadcast, or BV broadcast. We do it over gossip. So let's describe the main properties of binary value gossip. There are 4 of them. Before we can describe them, we will need to introduce 3 terms. I will introduce them now, but I will only define them later, as defining them requires a full description of binary value gossip. So, at a very high level, binary value gossip transforms individual nodes' estimates for a given binary variable into a set of binary values called bin values. Now, you may be thinking I'm just teasing you, but we will go deeper after explaining the 4 properties of binary value gossip. Obligation. If at least a third of the correct nodes BV gossip the same value, that value is eventually added to the set of binary values, bin values, of each correct node. Justification. If bin values contains a value, it has been BV gossiped by a correct node. Uniformity. If a binary value is added to the set bin values of a correct node, it will eventually be added to all correct nodes' bin values. Termination. Eventually, the set bin values of each correct node is not empty. This protocol propagates gossip events' binary estimates, for example an observer's metavote, to each node's set of bin values. Each node starts with a gossip event that carries an estimate for the binary value true or false. If any gossip event from a node sees estimates originating from over a third distinct nodes for the binary value that is not their current estimate, that gossip event's estimates becomes both true and false. If any gossip event sees estimates coming from gossip events created by over 2/3 of the nodes, this value becomes added to their set bin values. It's pretty easy to show that this protocol satisfies the 4 properties we just described: obligation, justification, uniformity, and termination. I will refer you to the request for comments if you're interested in reading the actual proofs. Now, with this binary value gossip protocol, ABA shows how binary agreement can be reached by using a common coin. To see it in action, let's start with this gossip graph that's already in progress. What happened before the rectangular gossip events doesn't really matter here. The only thing we need to know is that the 4 first round events are observers. The color in the bottom left quadrant of each gossip event represents the binary value they've observed. It's their original estimate for that variable. For example, it could be the value of their metavote for Alice. Green represents true, orange represents false. Now, we'll have the nodes keep gossiping between each other and see how the estimates propagate. Any value that has been estimated by over a third of the nodes will eventually make it to the bin values, thanks to the obligation property. Here, the set of bin values is represented by the 2 top quadrants of each gossip event. We should expect them to contain both a green and an orange cell eventually if we kept gossiping for long enough. So say Alice gossips to Bob. The new gossip event contains the same estimate as its parent, orange. It doesn't see over a third of green estimates, so nothing else happens. Let's keep gossiping, we may get luckier next time. Ah, this is a good one. Carol gossiped to Alice. And 2 things happened at once. First, Alice could now see both Bob and Carol's orange estimates, which added the orange value to its estimate in the bottom right quadrant. Then, Alice could now see her own estimate for orange in addition to Bob's and Carol's. That's 3 estimates, which is a supermajority. So, orange was added to Alice's bin values and made it to the top quadrant. Now Dave gossips to Carol. This one is much less exciting than the previous one. Carol's latest gossip can only see 1 false estimate that she's already aware of, and 1 true estimate which is less than a third. She only maintains her parents' estimate. But now we've got another good one. Bob already knew that Alice had created a gossip event that carried a true estimate. Now he sees that Dave has as well. This is more than a third of the nodes, so Bob's estimate now contains true. This makes it 3 agreeing estimates, so true becomes Bob's first member of bin values. Now, Bob had sent a gossip message to Carol before he received hers, but his message got delayed. She only now receives it. She creates a gossip event to record it, and what happens is similar to what happened with Bob's latest gossip event. She sees 2 green estimates, which convince her to add green to her estimates. This makes it 3, so true is promoted to her bin values. Note that the fact that we seem to add values to our bin values every time we add them to our estimates is only a particular case because our population of 4 nodes is so small that there is only 1 node separating a third from a supermajority. It's not a general rule. No, this one is my favorite. When Carol gossips to Dave, he goes from having no knowledge at all beyond his own estimate to adding both true and false to his bin values in one single gossip event. That's because he can now see Bob and Carol's estimates for orange, which add it to his own estimates and make it a supermajority. He can also see Alice, Carol, and his own estimate for green, which also makes a supermajority. In that case, when one gossip event has 2 bin values while its parent had none, we put the true value first by convention. Now Bob gossips to Alice, and the event she creates can see her own, Bob's and Dave's estimates for true. Alice adds Bob to his estimate. Following this process, every node will eventually be able to add any estimate originating from a third or more of the nodes to their decided values. One last little detail. Let me introduce a definition that will come in handy. If a gossip event has a non-empty set of bin values, the first gossip event in the set of bin values, remember that we said it would be true if they arrived at the same time, is called an auxiliary value. Also, remember that all of these colors are just a way to visualize our interpretation of gossip events. We're only doing regular gossip protocol here and assigning meanings so we can work our way towards consensus. We would have been diligent and come up with a common coin algorithm to close the loop, but then we learned of a solution that's much more elegant. We read the paper, Byzantine Agreement Made Trivial, that had been recently published by Silvio Micali from Algorand. Shout out to Antifragile on the Safe Network forums for linking to this paper in a forum thread and bringing it to our attention. It presents a synchronous Byzantine agreement protocol. As such, we couldn't simply use the entire algorithm. However, the key idea behind this paper is that creating an actual concrete coin is a bit too mathematical. All existing ideas involve solving some kinds of complex maths problem to generate each coin flip. By tweaking the way we aim for consensus just a little bit, we can replace the need for a magic common coin with that of a much more down-to-earth concrete coin. A concrete coin is like a magic coin, except it will only return a binary value that is common and unpredictable some of the times, say around twice out of every 3 attempts. The other times it can return any value, and that won't have any nefarious consequences. With the definition of auxiliary values in mind, substituting common coin with concrete coin is surprisingly easy. It only takes a little 3-step routine. We call that routine the full concrete coin protocol because computer scientists are notoriously terrible at naming things. The first step is called the forced true step. The second step is called the forced false step. The third and final step is called the genuine concrete coin flip. The forced true step starts by finding the oldest gossip event in the gossip graph that can see a supermajority of observers. We then apply binary value gossip until our bin values are not empty, at which time we have an auxiliary value, but we don't stop there. We continue binary value gossip until we see valid auxiliary values contained in gossip events created by a supermajority of different nodes. At this stage, 3 outcomes are possible. We may see a supermajority of valid auxiliary values true. Because this is the forced true step, if that's the case, we decide true and we are done. Binary agreement is reached as far as we are concerned. Each node is allowed one single celebratory glass of champagne when these conditions are met. We may see a supermajority of valid auxiliary values false. If that's the case, we will start the second step with an estimate of false, an empty set of bin values, and no auxiliary value for that step. Finally, we may see a tie, auxiliary values laid out in a way that there is no supermajority. If that's the case, we will start the second step with an estimate of true, an empty set of bin values, and no auxiliary value for that step. Something interesting about this little procedure is that if anyone decides true, they must have seen a supermajority of true auxiliary values. If that is the case, it's impossible for any other node to see a supermajority of false at the same step. This means that at the end of this stage, either no decision was taken or some nodes decides and everyone else has the same estimate. It will be useful to keep that in mind as we go along, since it is a crucial reason that makes this procedure works. Now that's it for the forced true step. The forced false step mirrors the forced true step, but creating an opportunity to converge on a false value. We start a new round of binary value gossip, gossiping the estimates from the end of the forced true step. When we see valid auxiliary values contained in gossip events created by a supermajority of different nodes, we stop performing binary value gossip for this step. At this stage, once again, 3 outcomes are possible. This time, if we see a supermajority of valid auxiliary values false, because this is the forced false step, we decide false and we are done. If we see a supermajority of valid auxiliary values true, we will start the third step with an estimate of true, an empty set of bin values and no auxiliary value for that step. Finally, if we see no supermajority, we will start the second step with an estimate of false, an empty set of bin values and no auxiliary value for that step. So far, we have explained the 2 first steps of the algorithm. By combining these steps, if all observers had had the same values for a given metavote, they would definitely all have decided by now. If that wasn't the case, if anyone had decided, all the current estimates would be in agreement. A third possibility is that no one has decided yet. In that case, the estimates could be any combination of true and false. In the last step, we will never decide on any value. But if the estimates are not in agreement yet, they will have over a chance out of 3 of agreeing by the end of that step. So, starting with the estimates from the end of the first false step, after seeing a supermajority of valid auxiliary values, we will update the estimates to true if we see a supermajority of valid auxiliary values true. Update the estimates to false if we see a supermajority of valid auxiliary values false. If we don't see any supermajority, we will flip a concrete coin and update our estimates to that value. Since the concrete coin has over 2/3 chances of being common and unpredictable, we have a chance out of 3 of reaching agreement at this stage. After this, we move on to the next round and go through the steps again, which means that if we have agreement now, we will reach consensus in the next round. Let's take a step back and look at what we've achieved so far. We have reduced the general problem of asynchronous Byzantine fault-tolerant consensus to the much simpler problem of finding a way to generate a random value that 2 out of 3 times is common and unpredictable. To do this, we first decided to use gossip to propagate knowledge through the network. We then assigned certain gossip events extra meaning, such as the observers. We showed that the problem of agreeing on the metavotes to consider, which is a binary consensus problem, is equivalent to the full consensus problem we set out to solve. With binary value gossip and the full concrete coin protocol, we showed that the problem reduced even further, to that of creating a genuine concrete coin flip, a pseudo-random value that has 2 chances out of 3 of being random and common. This is the last stretch. Let's walk through it. We're now in the last stretch for efficient, highly asynchronous BFT protocol. We'll need to get the concrete coin sorted. As we saw before, we are looking for 2 properties. The coin's result should not be predictable ahead of time. The coin's result should be common with a probability of over 2/3. To that, let's add a requirement. For cohesion and elegance, we would like for the genuine concrete coin flip to only use existing gossip events that would have been in the gossip graph anyway. No extra communication, no problem. Something that we can explain simply is how to convert a gossip event to a random binary value for the coin. Like any other kind of data, a gossip event can be hashed, which produces a big number that looks a bit random but is unique for any gossip event. If we write this number in binary as a sequence of zeros and ones and grab the rightmost digit, the least significant digit, this binary value is proven to be pseudo-random. It has a 50% chance to be true and 50% chance to be false. The proof for this is shown in the Byzantine agreement made trivial paper that we mentioned earlier. Now, I know of something that's got a probability higher than 2/3, picking randomly a honest node out of all the nodes. Note that the source of random here can be predictable, no fuss. So in theory, if we pick a random node and wait for them to create a gossip event that hasn't already been seen by other nodes before, every node could use that gossip event for their source of random. But there is one big no-no issue with this approach. If we picked a dishonest leader, they may just stop communicating at this point and stall the algorithm for everyone, spoiling all the fun. Here is an idea for a plan B. Assume we can rank all the nodes for any meta-election. Also, assume we could detect an unresponsive node. We could then pick the first leader and use the gossip event that carries their auxiliary value as the source of unpredictable coin value. Remember that the gossip event that carries a node's auxiliary value is unpredictable by a malicious node before the honest node, this node starts gossiping it. That makes it fit a crucial requirement of a concrete coin. If we didn't receive that gossip event and detected that the most leader node was unresponsive, we could then pick any number as the value wouldn't need to be common or unpredictable. We arbitrarily decide to pick gossip event carrying the auxiliary value from the most leader node we see. So we now have two remaining tasks: assigning a leadership rank to each node, detecting a node that's unresponsive. With this in mind, we'll need to cut before. Knowing a few primitives, we can make up that gradient leadership without much hassle. First, let's remember that a hash function produces a pseudo-random number from any piece of data in a way that the number will always be the same if the data is the same. The XOR distance is a measure of distance between two numbers that has the crucial property of being unique. Each node has a unique identifier. With this in mind, if we create a hash that is unique to the circumstances we are targeting by hashing together the hash of the public identifier of the nodes that's subject of the metavote, the hash of the latest consensus event, and the round numbers hash, and if we sort the nodes by the XOR distance of their unique identifier to that hash, we obtain the gradient leadership we were looking for. So this approach provides us with an order that's unique to each meta-election of each round for each new network event being decided on. It may sound a little complicated, but every part of this little procedure is very well-known mathematics, so it's actually quite easy to prove the correctness of this approach. Having figured out the gradient of leadership, let's now tackle the issue of a node's responsiveness. I don't know about you, but this all feels like progress to me. We are now down to one last piece of the puzzle to figure out: how to detect that a node is unresponsive. We need to use a property of gossip, as any use of timers would make it impossible for nodes receiving our gossip later to understand why we decided to ignore the most leader's gossip. It would also bring more synchrony assumptions than we are willing to make. If you remember, when we originally defined gossip, we mentioned that some gossip events would be gossip requests, and some would be gossip responses. We make the following synchrony assumption. The time taken by a request-response cycle between two honest nodes only deviates by a random amount amongst any honest node. This way, if we wait to receive enough responses to gossip requests we initiated after a certain point, we can be sure that the most leader node would have answered if he was responsive with a certain probability. We call the number of responses the responsiveness threshold. From previous research on gossip, we know that a number in the order of log of n will suffice. And the loop is closed. I had two goals when preparing this presentation: explain why PARSEC is unique, give enough of an overview of the maths to completely demystify the algorithm. I hope I did a decent job at it. Thanks a lot for listening. If you're interested to learn more about why we released PARSEC in the open and what it means for the wider field of distributed systems, you may check out our introductory blog post on Medium. If you'd like to understand it at a deeper level, I recommend reading the request for comments. If you're not afraid of mathematical notations and you would like to understand the proofs in details, do check out our white paper. I was invited to an episode of the Safe Crossroads podcast with John Ferguson, where we discussed the implications of PARSEC for the crypto space. If you're not tired of my French accent already, you may find it interesting. Please, do join the technical discussions about PARSEC on our developer forum. We welcome any feedback you can share with us, if you can find a way to make PARSEC even better. If this presentation made you curious about Maidsafe and what we are trying to accomplish with the Safe network, you can find more information about the company on our website. You can join our welcoming community on the Safe Network forums and take part in the discussion. The Safe Network Primer, which was written by members of our community, gives an excellent overview of the Safe network. Finally, if reading all these gives you the bug and you want to contribute in developing applications for the Safe network, please check out our developer hub. That's all for me. Thanks.